from Oak Ridge National Lab.
This
And
meeting is being recorded.
okay, we all know we're being recorded, so let's be careful and not wander into any NDA areas. I'm Susie Titchener with Oak Ridge Lab, and along with David Martin, my colleague, who's also here, we co-manage the ECP Industry and Agency Council, which is a group of industry and federal agency executives that provide advice and guidance and input and into the leadership of ECP on their needs and directions. And it provides a very, very interesting dialogue. And our session today, the on-ramp to ECP software and applications, actually is an outgrowth of some of the discussions that we've had at the Industry and Agency Council meetings. It's a topic that was of a lot of interest to our members. And so we thought we'd set aside some time today to talk about that. So thank you for joining. We ask that everybody just manually mute yourselves. We're not going to do a global mute so people can ask questions when they need to. And also, please feel free to put your comments and questions in the chat, and we will be monitoring that too. David?
Yeah, so I just got the slides. I will upload them to a box folder and post it in just a few minutes. The format is basically a chance for both Mike and Andrew to talk about their approach to the on-ramp of both ST and AD products. And then we will have an open dialogue that is led by Pete Bradley from Pratt & Whitney Raytheon Technologies. So hold your questions kind of to the ends of the talks, and then hold your kind of general comments, I guess, to the roundtable that we'll have at the end. Feel free to post things in the chat, and we will make sure we get to those during the discussion time. So Pete, you want to kick us off and introduce Mike? And you are muted if you...
Yeah, the introductions work much better without the mute button.
There you go.
Thank you everybody for joining. I'm Pete Bradley, fellow high performance computing at Raytheon Technologies, Pratt & Whitney, and currently wearing a second hat as the acting lead for our digital tools and data science discipline. I'm really excited about this topic. I think one of the things that it's just a very different way of thinking about software coming out of exascale compute of supercomputing projects from previous generations. And today we've got Mike Rue and Andrew Siegel, who are going to talk about their respective areas. And then we're going to get a chance to chat a little bit and do a deeper dive on the on-ramp for software. So with that, Mike, are you kicking off?
Yeah, I think that's the order. I'm happy to do that.
Excellent.
All right. Well, so I have just a few slides, kind of some maybe initial framing comments. By the way, if you're looking for really deep stuff like on OpenMP with target offload, there's a session that's competing with this. I think it focused on Aurora and OpenMP experiences there. And so I won't be offended if you go and visit that session for that level of detail, because we're not going to get here, at least in my comments, to that level of detail. We're going to get more about kind of overall strategy and approaches and maybe into details in some of the comments. But just
Mike, as a moderator, I have to tell you, you're not supposed to sell other sessions in the middle of our session, all right?
I'm sorry. I just want people to be satisfied, in a holistic.
Fair enough. Fair enough.
All right. So a little bit of an outline here. And I'll get moving. Okay, so the not now lift, the light lift, the heavy lift, and then what I'm calling the E4S two-step process. All right, so what's the not now lift? Well, if you wait long enough and avoid the bleeding edge, the software ecosystem will become more usable. There's a really nice collection of content, primarily driven by Jeff Larkin at NVIDIA. As far as I know, there are probably other people voicing a similar philosophy, but this is just a link to a talk and a paper that he has on this. And the basic, the theme of this kind of approach is that everybody wants to make these devices and these discrete devices more usable by a broader audience. That's how the vendors make money. That's how scientists are become more productive. And so if you don't need to be on one of these machines right now, if you do not have a mission or a business case for it, I just want to say up front, just don't do it yet, because there are two things that will happen. You don't really need it, so keep going with the approach you're using. Or and in addition, as time goes on, it'll actually become easier to get onto these systems. And so if you want a kind of a hint of how things might go in the future, checking out what Jeff Larkin has stated here could be a good thing. Now, practically and realistically speaking, the approach that Jeff is describing here isn't really available to people today for the most part. NVIDIA is probably further along than most. They have a very mature software stack. But if you're interested in being executing across multiple accelerator devices, which is, for example, the mission of ECP, this approach isn't available to you at this point. But again, I mention it kind of as a holistic view of what we're trying to do here. Okay, what's the light lift? This is offloading high cost computations to GPUs. So this worked for a long time. In fact, in the early GPU systems, if you look at like the history of what was available at Oak Ridge, they've had multiple generations of GPU-based systems. They made sure they had really beefy CPU systems so that the apps that couldn't make use of a GPU could still do well on the platform of the day. And in my area, where I've done a lot of direct work, R&D in sparse iterative solvers, early GPUs were really not that competitive with CPUs, especially if you throw in the complication of having to migrate all the data and the computation to the device rather than just staying on the CPU. But really starting with the V100, which, the Summit platform, this was no longer true, even in my area, which with the sparse iterative solvers, which is one of the more challenging areas to obtain good performance. And also I think everybody generally sees that this will be less true as we go forward. There's just too much computational and memory performance on the GPUs, to ignore them for the work that we're doing. So what's the heavy lift? This is moving all consequential computations to the GPU. I'm guessing Andrew might show, he has a very nice diagram of kind of the progression of how things have gone. And if he shows that, you'll become more apparent with a graph. But this is, I think, necessary for most codes today. If you have the resources to invest in it. We had a nice set of comments from Dan Stanzioni from TAC about the challenges of this approach and how, at least for some, his user base, it may not be necessarily the right thing right now. This is the kind of not now approach. It requires a very heavy investment in user code, because now you've got to take all of your code, every loop block, anything that does any kind of consequential computation or data movement, and get it onto the device and keep it there. And so it's a very a labor intensive activity, depending on how many lines of code you've got to port. In my experience, it's mostly been about taking any loop structure that you have and transforming it into a parallel for or parallel reduce or parallel scans. Parallel scan is less commonly used, but for sure parallel for and reduce are commonly used. And you might have nesting, so you could get better performance out of teams of threads. And so a lot of the effort that goes into porting an application goes into restructuring your code to take advantage of these loop patterns, and making sure that when you say that a for loop has every iteration can be done independently, that's really true, that you don't have some kind of convenience code in there that breaks the parallel for and that you sometimes have to, in a very consequential way, restructure or generate a new algorithm that is, scalable parallel in this way. So some of the choices to help you with this effort in your code is to use abstraction layers like Cocos and Raja. These are both layers that allow you to use them as libraries and to re-express your code in a form that Cocos and Raja can then compile and transform for whatever given backend you have, whether it be a CPU, a multi-core CPU or a GPU, of various flavors. And so that's one approach. OpenMP with target offload is another approach. We're still seeing stabilization issues, with the implementations of OpenMP. Another is OpenACC. In a sense, a competition with OpenMP. There are business strategies around OpenMP and OpenACC, which are not, I consider not necessarily optimal from the users community, but these are companies that are running a business. They have strategies around one or the other of these approaches to do similar kinds of things. There are certainly also philosophical differences between OpenACC and OpenMP. Another approach is to do homegrown isolation of your kernels, with the app team developed adapters. And I'll show you just a little bit of an example of that. And then, of course, you can do combinations of these things. You can, for example, use OpenMP by default and then customize for CUDA, HIP, SYCL, or whatever for really important kernels. And so that kind of blended approach can be appropriate as well. To just give you one example of what's going on within ECP, this is the math libraries area. So these are a bunch of the libraries from the math libraries, the so-called XSDK, the math libraries SDK. And so, this is their, status on NVIDIA, AMD, and Intel. This was a few months ago. And, so the, maybe a little bit dated, but it still serves the purpose I'm trying to show, which is, strategy one is to isolate performance impacting code to select kernels and then write your own CUDA, HIP, or SYCL kernels. And so if you look at the Ginkgo library, Hefty, Magma, MFEM, Slate, Strumpack, SuperLU, and Tasmanian, they've all done this. What they've done is they've said, okay, where are my compute-intensive kernels? Let me, collect them. Maybe I'll generalize them a little bit so that I can reuse the same code for multiple similar type loop computations. But then anytime they port to a new architecture, they have to implement a new version of each of those kernels, for CUDA, for HIP, for SYCL, for whatever else would come along for any kind of new device. Strategy two is to use one of these translation layers or portability layers like Cocos or Raja. And the libraries shown in green use those approaches. And then there's blending the two, and you can, for example, Hyper, PETC, and Sundials provide, both types of approaches where they have, customization for the node specific library like CUDA. And then they also have, say, a Cocos or a Raja layer that allows them portability for things that they don't want to write, especially in say, CUDA or HIP. And so anyway, these are just a few examples of the kinds of strategies that you would want to consider if you are going to migrate to a GPU or portable GPU like environment. So what's the E4S two-step process? So it may not be clear, but E4S is actually a very capable software stack for MPI CPU codes. And so if you want to execute on top of, say a more, standard HPC Linux cluster with, x86 multi-core CPUs and, no GPUs to speak of, if your code is already running well in that kind of environment, you can actually migrate already on top of E4S and use the libraries and tools that are part of E4S, via calls to the libraries that are in the portfolio. In particular, you can, do one of these performance portability strategies. You can write on top of Cocos or Raja, for example, and rewrite your loops in terms of these libraries, these portability layers, and execute on a CPU platform with multi-threading and some vectorization support. Teams are working on that. So side by side with all the GPU work that's going on for ECP, all these libraries and the tools already support CPUs. We even can execute, I wouldn't say our performance is great on things like the ARM, the AF64FX processor that's in Fugaku, where we don't have a good performance so far as I can tell is in vectorization, which is really essential to get good performance out of the ARM SVE instruction set, but it runs. And so you can migrate on top of the libraries and tools that E4S provides in your stable CPU cluster environment. And so essentially what you're doing is you're breaking this process. I have to migrate my code both to a new software stack and to a new platform at the same time. You're breaking that into two distinct steps. So what are some benefits? Well, migrating to E4S on the stable platform, you can start using SPAC if you're not already using it. It's a great meta build tool, including for your own software and the tools that you manage. If you tap into the SPAC build caches, rebuild times we see generally go down by a factor of 10, because what SPAC will do is it'll remember any build of a signature in the build tree that it has done before, and it'll pull in that binary for you rather than rebuild it. And it can be a really nice way of speeding up rebuilds. You can have a single point of access to the documentation, the doc portal that E4S provides. And in general, we're trying to elevate the quality of our software, the products that are part of E4S, by our support structure and by our commitment to quality. And then this is a preparation then for step 2. And what is step 2? Turn on the GPU build. It's much harder than just doing that, but it is in fact that kind of activity. And so you build with the GPU backends, especially if you're using Cocos or Raja. A lot of teams have had success in this two-step process because the ease at which you can swap backends and your code stays roughly the same. You just build with a different back end being generated. And then what happens is this transition to the GPU platforms becomes more a debugging and adaptation exercise than it is this heavy lift of restructuring all your code for a portability layer. And then you can also track the growth that we're in E4S GPU capabilities. We have a tremendous amount of efforts going into improving the GPU capabilities in E4S in our various products and the performance of those GPU capabilities. And so you can track those because you're already building on top of the E4S software. And then furthermore, I mentioned in an earlier talk, I won't go into a lot of detail right here, but you can interact with the E4S commercial support team. So we've contracted with a company to provide support for E4S for DOE facilities and teams. This is a private company, and they would be open to a similar kind of arrangement with you if you wanted to pay someone for support. Also, this team can do something, at least as time goes on. They may not have the expertise right now, but I foresee them getting the expertise. We've had many people in industry ask us, hey, you've got all these different solvers. Which one should I use? That's really hard for us to do. It's kind of like, having an Apple person and a Microsoft person in a room and asking them, hey, should I buy a PC or a Mac? It's not really a fair question to ask. You want to ask somebody who's not invested in the development of one of these, but still has knowledge. And so I would foresee that the support team, because of the interactions with the various products that are part of E4S, could probably give you some unbiased advice about what to pick. And I think that's it.
Great, thanks, Mike.
Yeah. I hope that was what you were looking for.
Yeah, I think especially the conversation about what support structures there are is really useful.
Yeah.
Yeah.
Do we have some clarifying questions for Mike before we go on to Andrew?
in the chat here. Oh, that's just a comment. Sorry, from Al. It's not a question.
Yes.
Let's see. Did you see the question, Mike, from your?
Oh, do I have a
It's at the
question?
top. Do you think
Oh.
CPUs with HBM will move the needle back towards CPUs?
Yeah, Al responded already with a much more precise answer than I could give. So,
Okay.
yeah, I don't know, Al, maybe you can say it. I don't see it going back. Do you?
No, it's not going to be able to move back at all. It's a,
Yeah.
as the answer shows, it's a factor of 10.
Yeah.
Sometimes as much as a factor of 100 when you start building these bigger machines with multiple GPUs per CPU. It's much more than just the performance.
Yeah.
One of the things that GPUs have done is allowed us to have a tremendous improvement in energy efficiency of these machines. So you can get the same amount of work done and save millions of dollars for your industry in energy costs of running that computer by using GPUs. And that's a secondary advantage that's just going to make it really hard to move backwards towards CPU only.
Jörg, are you comfortable there? Do you feel you got your question answered? I will take that as a
You're
yes.
muted,
There you
Jörg,
have
if
it.
you're trying to talk, but
He
Well, he
just
said-
responded
Yeah,
in the
I think
chat.
He's
Good.
found it in the chat.
Yeah,
There
I
we
think
go.
I think it makes sense. I think for some of the applications that have limited budget, those HBM CPUs might still be very attractive as a stopgap.
Yeah,
Right. If
I
you don't
mean,
have,
personally,
have a lot
I'll
of
be the
people-
contrarian. I think that there's a huge potential for some of those architectures to address the issues that, like, were talked about in one of the earlier talks around moving some of these legacy codes to address some of the performance issues that they're having, and not having to rewrite all that code. So I don't know. I think there's going to be a potential for that.
I think in Mike's two-step process, I think it's sort of first step 0 or a half step instead of getting to step 1.
Yeah.
Well, not everything can leverage E4S for the majority of its performance, but I think that it's not just about the cost of rewriting code. There are certain computational patterns which more naturally fit on CPUs, right? It's not, and maybe with a really heroic effort, you can get reasonable performance increases on GPUs, but I think there's sort of a natural self-selection, even when you factor out the amount of software investment to port to a new system. So,
Yeah, I mean, I agree with that too, Andrew. That's a really good point, because there's several of our applications, and when we benchmark them, with all the optimizations, they still perform better on some of these CPUs.
Mm-hmm.
Yeah.
it would boggle your
Remember,
mind.
also in industry, yeah, I was just going to say in industry, you've also got folks who have codes that have been validated over the past 25 years, supporting products that have been around for longer. And so things like that, where the it's not actually the cost of the software, it's the cost of the validation really makes it prohibitive. And so that's an area where I think you'll continue to see that.
Validation.
That's why the not now slide is there. Right.
Yeah.
Charlie, tell folks the company that you're with, so especially Andrew has a contact for some of your comments.
Sure, sorry about that.
Charlie's from Exxon.
Yeah, I'm with ExxonMobil.
So I just wanted him to have the context for, are you talking like seismic or reservoir simulation?
Mostly seismic, but I mean, I think that we, some of the reservoir simulation codes too have seen the same kind of issues.
Okay.
Interesting.
Yeah, I mean, for me at Boeing, in the CFD space, we certainly are moving towards GPUs. But I mean, on our internal system, I have 2,000 users with probably 150 or 200 applications. I just don't have the bandwidth to modernize all of those applications. Like especially if these are applications that have only a handful of users. And so, yeah, I think the not now lift is going to be an important aspect, at least in industry.
Yes.
Great comments. Any others before we move on to Andrew's talk? Andrew, why don't you take it away then?
Okay. All right, well, I'll start by saying we do not have an E4S for applications. So the strategy for on-ramping is complicated. And I'll give a few different perspectives as starting points for conversation, but nothing as definitive as what Mike was able to say. Question to make sure that we're on the same page. I've spelled ECP wrong, sorry. As ECP is wrapping up, how can groups outside of ECP leverage all the investments in these applications? Okay, so for 7 years, we underwent this radical transformation, which I'll have a slide on that I just slipped in momentarily, but Mike alluded to it. You know, this going from multi-core CPUs all the way to GPU resident codes on a diverse ecosystem of GPU, multi-GPU architectures. So most of the apps are open source. They can be distributed and adopted. That's not a problem. Repositories currently are not centrally managed by ECP. I have some vision to create an organizing portal to them in a centralized place at the end of the project, but that's a relatively small step, and at least it's sort of a starting point. But what other plans are there to facilitate the adoption, and what are reasonable expectations, and what do we care about, and what do our sponsors care about? So I think we all agree within ECP that to the extent that it makes sense, it's very important for us to have an enduring impact of application investments. Okay, and that implies a lot, such as what happens to the applications after ECP ends in terms of sponsorship or whatever. But we would like to leave ECP with software on the application side that can be used both by the application developer groups who develop them, as well as, where appropriate, external application communities. And that can be actually very broad when it comes to physics components that are cross-cutting across many different domain areas, very fundamental physics components. So we envision usable apps that are relatively robust and well-engineered as code artifacts leaving the project. And I guess one question that we have is our current structure and our current investments and funding allocations and incentives within the project adequate to produce that? I'll have some thoughts on that later. And then what can be reasonably expected of each application project? And I'd like to interpret the idea of somebody using an ECP application a little more generally than downloading it and building it and running one of the configurations that can be run. It could be adopting the source code, experts in the field who take functions or the entire code and fork it, start to develop it themselves. There can even just be ideas and approaches for how to port certain algorithmic patterns to GPUs that can be taken in small part or just as the idea itself and recoded, or it can be a componentized application, can have particular infrastructure that is adopted, but not the code as a whole. So I don't think we want to think just about using it as a piece of software. And I want to make some observations about why it's a little bit more difficult to discuss this for applications and some fundamental differences between what I think of as enabling software technology and applications, understanding that there's some overlap at the edges, but they're fundamentally kind of different phenomena. So software technologies, sort of by design, preferentially target infrastructure that is common to many apps. This simplifies identifying a user community, like who would even want to use this, while you've already identified motifs or commonality among applications as the motivation for developing it in the first place. There are a lot of instances of successful application-specific software that's very valuable. So things that really target a specific application or very small class of applications, like the tensor contraction engine or something. That seems not to be the preference. I think most people are interested in breadth of impact, and others can correct me if I'm wrong, but there seems to be a premium on broad adoption and identifying abstractions that have impact across a very wide swath of the HPC community. software technologies are typically more robust. So they have clearer input-output contracts, fewer heuristics, and there isn't really the concept of validation as the ground truth. As you continue to validate an application code, you are always learning more things that it doesn't do well and that it did do that you didn't think it could do. And so it never ends in a sense. You're constantly changing it. And it's not really clear what the endpoint would be in most cases. And I think that it's less typical for what we consider software technology to be in that realm. So applications tend to target scientific discovery usually ahead of the tool itself. Oftentimes the tool is accreted through the solution of many new problems. So somebody has another problem they want to solve, you have the computational components to be able to address it. You modify them, extend them a little bit, you solve a new problem. Then through iterating that process, the code kind of accretes capability beyond what you necessarily even intended it for originally. And it grows in its potential user community. Often for applications, getting the answer is just the starting point for scientific discovery. It's not an end in itself. When I say getting the answer, when you conduct the simulation, it's rare that you say the eigenvalue is 1.01 and that's my answer. There are use cases like that, but more typically it's thought of as a data set that is the beginning point of trying to understand physical phenomena that impact your application field. Where there are cases where the methods are more general and broadly applicable. And in that case, you could have very broad user communities for things like molecular dynamics or computational fluid dynamics, structural mechanics, transport methods, where the methods are tied to very specific applications. So there's sort of another side where you're really focused on solving a particular problem. You have a lot of heuristics and the models are very specific. You might only have a user developer community and small collaborations with other research teams in the same area. So it really represents a wide range of different types of software artifacts that are generally different in flavor than what we think of as ST. Okay, so I won't go over this, but I just thought it would be interesting to see, one, what the different areas are that are funded in ECP, just as a blurb, and then how disaggregated the sponsorship is, and why it's hard to have sort of a uniform vision of this, because no single entity, no single agency, or no single office owns domain science. It's spread across many different areas, and they each have different motivations and different drivers and different incentives, and that creates different outcomes. So we have a portfolio of energy applications. We have wind turbine modeling, small modular reactor design. We have plasma optimization for plasma wave field accelerator design, carbon sequestration, combustion engines, fusion for tokamaks, so magnetically confined fusion plasmas, a portfolio of chemistry and materials as quantum chemistry, molecular dynamics. We kind of fit lattice QCD in there because it's sort of small stuff, even though it doesn't exactly fit others. Electronic structure, additive manufacturing, so things in the realm generally of materials. We have Earth and Space Sciences that includes astrophysics, cosmology, wellbore modeling, seismic, climate, and so forth. And then we have these sort of really interesting set of non-traditional HPC applications that are more data-driven. They, in a lot of cases, I will say not for the machine learning, but for the top 3 cases, they are not natural fits to GPUs. The metagenomics are just distributed hash tables everywhere, and there are very few floating point operations. There's a lot of string matching, and you have to work really, really hard and be very clever to think how to take advantage of GPU architectures for that class of applications. And similarly, it's a little different for doing real-time image processing from light sources, but these are data-centric and outside the realm of what we normally do in HPC, and they bring up a lot of interesting motifs that are challenges on GPU architectures. Okay, and Mike mentioned the slide, so I thought I'd slip it in as he was talking, that all of these application projects that are funded with ECP have undergone this 6-year to this point transformation from multi-core, well then to many-core CPUs sort of right at the beginning, to that CPU plus GPU, where as Mike said, maybe it was 50-50, the total performance that was accounted for by each, to CPU plus multi-GPU, where it was becoming more dominant, the number of flops supported by the GPU, so that people moved to GPU resident algorithms that sort of mics all in, to diverse multi-GPU architectures when we learned that we were going to have NVIDIA, Intel, and AMD processors, to very specific optimizations for whatever architecture the team is currently targeting right now, which a lot of people are Frontier, because it will be first exascale system. And it has unique features to the MI250X processor that you need to tune for to get that last bit of performance. So let me talk a little bit about community codes versus developer end users when I think about what to expect in terms of on-ramping. So the way I see the AD projects, there are three really broad classes. You can't put them all together under one philosophy. There is the sort of class where the core code developers are the end users. So the people doing the research in the field are the ones developing the code, and the code itself is a research test bed, working on new model, new phenomena. And the principal focus is on solving very specific problems, simulating very specific phenomena. Building, verifying, and running code is very much the starting point. Most of the work of discovery is done by analysis of the data. And end users from external groups are relatively low priority. You might have some collaborations, but generally you're really focused on doing your own research. We have a class where core code developers include domain specialists who might be end users. And then there are other people contributing. There might be applied mathematicians, computer scientists, research software engineers, and they're using the code for their own research, but they have an eye on a community code. This would be true, say, of the Fusion project, who aims to deliver a whole device model to the Fusion community, or to the climate community, who is developing for broad swath of climate researchers one community code. Right, so there's an emphasis on making the codes available to external research groups. And even though it's not explicitly funded to sort of package the code and document the code and train people, it is in a sense implicitly funded as a sort of understood part of a large enough budget where there's money to and time to do things like that. And then there's this really interesting third class, which is not common, I would say, but which you could see a little bit, particularly in those new applications that I listed on the last page of applications. And that's where the core code developers are not the end users, and maybe not even active researchers in the domain. And it's a little bit more like software technology in that sense, where you are building a capability for other people to use. So for example, the metagenomic sequencing tool is used by the people at the Joint Genome Institute, who might sit right beside the developer. But the developers are really focused on the computer science aspects of the problem. And because there are so many heuristics, there has to be a lot of back and forth between the two groups for the developers to make it useful for the domain experts. I would say there's a non-standard model. Drivers could be, though, very interesting applied math and CS challenges like distributed hash tables on GPUs. And the use cases are fairly robust, relatively speaking. And it's a less common model, but we do have some of that. Okay, so what about the motivation to build code for other people? It's traditionally, I'm generalizing, but it's not seen as a central focus of funding decisions when code groups go to, seek more money through funding announcements. And it, might sound good in a proposal as a side benefit, but I think most people recognize that you can use it, at least in some nebulous way, as leverage to obtain new funding. So if you have hundreds, in some cases we even have thousands of users, for example, for quantum chemistry codes, it's, I think, a very good demonstration of its impact. People also have a lot of personal pride in having others use what they develop. So they're willing to do a lot of work on nights and weekends, and things that aren't explicitly funded, to a point of what's reasonable to have the benefit of other people's code, which could be making the code better itself, understanding limitations and things it can do, as well as sort of demonstrating its impact. And there are occasional examples of program offices supporting community codes more strategically. Okay, so there are many examples in ECP, and I've just picked a few random ones, of applications with both external and internal user communities. So we have a computational fluid dynamics code, NEC, which is doing problems in geophysics and astrophysics and wind turbine simulations and all different fields. Carl and neutron transport, MCMP was a good example of this traditionally. Now we have shift and OpenMC, we have quantum chemistry, electronic structure, and we have other application-specific motifs. So there is definitely a class of applications that seek external users and which can be adopted broadly across many different domain science fields, not just within one set of problems. And I'll give climate as an example, the community Earth system model of a community effort for researchers within a specific domain. So examples abound. I'll say one thing really quickly. I just want to make a final point. I'm not going to show all of this, but for on-ramping ECP applications, sort of plan zero is that we have baked into ECP the formal verification of our KPP. So without reading lists, let me just be clear about what we have to do. The applications in the application development part of ECP have to demonstrate that they can successfully execute a challenge problem on the exascale machine at certain performance level, and all of the artifacts that are required to reproduce that challenge problem have to be clearly documented and signed off on by an external referee, a subject matter expert. That's what SME stands for. So if you just look at the highlighted bullet on the sub bullet of the third bullet, the KPP1 and KPP2 runs, those are the sort of formal project verification runs at the end of the projects, have to be fully documented and reproducible, including any caveats. So we have, in addition to sort of portal to all of the applications that have been built at ECP, we have a very clear contract and set of rules for anybody to be able to take the code and reproduce the flagship challenge problem that was done as the sort of capstone accomplishment of the project. Okay, and we expect this to provide a starting point automatically without doing any extra work for anybody who wants to be able to do the simulation that was done as part of ECP demonstration of success. Okay, what about more robust on-ramping support behind that? That's just sort of a first level. So I think we face the question of, should we explicitly be directing funds toward facilitating external use of ECP applications beyond this? The risk we run is that many teams, in order to do this toward getting the performance they need to meet their KPPs on the exascale systems, have not re-merged their development branch with their production branch, particularly if they have an active user community. So to what extent do we want to ensure this happens, and at what level of robustness? So I think there are different solutions for different classes of applications, and we need to consider applications in different pins based off of the size of their user communities. But you know, toward the end of the project, we're going to be emphasizing documentation, software hardening, examples for users. Possibly, we don't have answers to these questions right now, but how far do we take the idea of offering external user support during the final stage of ECP, and then even after that? I'd say these are open questions. Then who would do this? So I think development teams are sufficiently incentivized to invest some fraction of their time in having the adoption of their code by external groups. It's going to range a lot depending on the domain, but I don't think that most of the time will be spent doing that. So that raises the issue of outsourced code maintenance. So we heard in the last session a few successful examples of people who took not the core software engineering of the code, but particular maintenance tasks that weren't attractive to people who were doing research with the code and outsourced it to professional software engineers. So there are other possible ways of leveraging what's been built. I mentioned adopting the code and forking and dealing with it on a source code level. And then there is just the idea of not the codes themselves, but some of the things Mike talked about at the beginning, which is the lessons to be able to take things that you have and not have to go through everything we went through. So there's the natural maturation of all the software, but then there are a lot of lessons that I think if we passed on to people who came after us would save a lot of time relative to what we had to do. And thinking about small codes and test beds as exemplars of what works and what doesn't work could easily, we've had a sort of mini app effort as part of the ECP project that provides a lot of the direction for being able to do some of the things yourself. So, complicated topic. Those are just some thoughts for point of discussion, but I think I'll wrap it up there.
Andrew, thanks very much. You've presented a very different business model, if we want to call it that, that AD has than Mike's team and ST. And I think the contrast, the compare and the contrast that you've done here has been very helpful and illuminating. We have time here for a few questions specifically for Andrew, but I think what I'll do is, Pete, why don't I turn it over to you to moderate those questions and then pick up on just kind of the roundtable discussion that we had planned here for this next section.
Sounds great. So I guess what I would just ask is, if are there any questions? And if we have too many, then we'll go to hands raised. But any quick questions before we move on to the next part? All right. Well, thanks. I think what we're going to do next is kind of get into a little bit more of a roundtable discussion. I've got some questions that I'd like to ask that I think will be of interest. I would encourage people, if you have comments or questions, to put them in the chat as we're talking, and we'll try and work those in as well, or we'll bring them in at the end as well. So I'm just going to kick this off. You know, I'm coming from industry, and I know we have a lot of industry representatives today. But I think we can look at it more broadly and say, you know, for those of us who've been watching leadership class computing system projects over the years, ECP has a fundamentally different way of looking at software, I think. I think there was a lot more focus on the machines. There was a lot more focus internally. And so my sense is that there's much, much more focus on software as an enabler and also externalizing that. So without leading the witnesses any more than that, I guess what I'd just like to ask both of you, because I think you'll have a little bit different answers, is, you know, what are your targets as far as onboarding of software for other users? And what does success mean to you overall for the software aspects and application aspects of this program? Like, what would something where you would say, yeah, this was really successful, you know, 5 years down the road?
I can get started, Andrew. It looks like you're thinking.
Okay, go ahead. I was waiting for that. Yeah.
Okay. I was waiting for you. That's what is that? A deadlock, right? Anyway, so I mean, I'll go back to the kind of big missions of DOE, which is, you know, we have, you know, science objectives in, you know, energy, broadly speaking, national security, you know, advancement of science for the nation, you know, not uniquely everybody, you know, there are a lot of other organizations, but, you know, all of our efforts have to, I think, in the long run, you know, be able to point to this, you know, encouraging the success of DOE's mission. From my perspective, more specifically, I think, you know, the DOE has, in a certain sense, the privilege, you know, over many decades of being able to do a lot of fundamental algorithm and software design and development, you know, in ways that other agencies, for example, within the US, don't have as much. I mean, there's certainly development, but if, you know, it was a theme of the day, you know, that a lot of other agencies don't have, you know, the same resources or mission that we have to fundamentally rethink how we're going to do our application and software environments. And so it's a privilege we have to produce this. And what I'd like to see, and hoping that we're doing to some extent, is also make what we do available outside of DOE. I think with a modest amount of additional effort, planning, you know, processes and workflows, we can make a lot of the work that we do available to US industry, to other US agencies in a way that's, you know, valuable to them and reduces the gap enough between, you know, what we would do just for our own purposes and what could be usable to you, you know, so that the leap is not too big. for you to benefit from what we're trying to do. So in a kind of a big picture sense, that's what we're after. And so we're trying to, develop not only technical approaches, but also business models that would support us in that kind of objective. I'll stop there. Yeah.
Okay, well, I'll mention some other things. Doug, I'll point out, put in the comment that he wants a Nobel Prize directly tied to insights gained from one or more of the applications. So I'll give a toned down version of that. And I'll say that the challenge problems, which are the kind of capstone simulations of ECP, which were vetted early in the project as impactful in the fields, would uncover new scientific insight, and that would be demonstrated in the literature and accepted in the community. And a number of the different areas that we funded. That would certainly be one that's very important. Another is that we pave the way for people who come after us. So, a lot of this that I don't think I fully appreciated at the beginning is a co-design struggle with the system software, with the compilers, with the runtime, and trying to work with the vendor to figure out, what is working how well and how it can be changed. And the ultimate demonstration of that are a lot of these massive, complex multi-physics applications. So the intent would not be, and Mike alluded to this at the beginning, for everybody to have to put in the effort that we had to put into. That is no doubt, partly includes a lot of co-maturation of the systems themselves. And that could also be encapsulated in code artifacts and lessons learned that help accelerate other people's adoptions of the system. And the third, this might be setting the bar too high, but I'd really like applications that were developed, as I kind of alluded to in the next to last slide, to be something that someone who has, say, a GPU-based system, let's say multi-GPU nodes, even a modest number of them, could download and reproduce, execute, reproduce the results of some test simulations of as a starting point to adoption. You'd be very, very surprised at how much interest there is in utilizing even codes that solve very specific problems. I was just hearing a talk this morning, I mentioned earlier, about our ExoWind project, who does wind farm modeling, so turbine atmosphere interaction. And GE adopted the code to look at some behavior of the wake of offshore wind turbines. And it's not, leveraging a lot of the software technology that Mike talked about. It's not an unreasonable lift to be able to access and use some of these codes for slightly different use cases. And I would set that as a goal. And it's just hard to speak totally generally because there's such a vast range of different applications, but that would be the hope at the end of the project. And I think we have to, at a management level, kind of steer and direct things in that direction, because focus has really been on running on these machines, developing the new capability to run on these machines, and getting the performance that people need to formally succeed in the project. So those are 3.5 things that come to mind.
Excellent. So, I think both of you are talking a lot about adoption and industry adoption, and that's really, I think, one of the great things that can come out of this project. If you think about industry adoption, it's going to require a few things. It's going to require that the value of the software is there and recognizable to industry and communicated. And that the different options are communicated as well. We talked a little bit about, you guys mentioned that earlier. And of course, we've also talked about having a viable support life cycle for that long term. So I guess we've talked a little bit about how you're going to address those needs, but I'd like to just put a little bit of a different spin on it. The gap between leadership computing and everybody else has never been greater than with the ECP. And that's by design, but on the other hand, I think it's another challenge. So even as there are spin-offs, making that connection, I think, is hard. So I was wondering if you could just kind of speak to how that value can be ensured and communicated, and then what the support life cycle looks like going forward. If, for example, I'm an industry person, and you're looking at the next, whatever the next generation machine is. Mike, do you want to go first?
Sure, I can go. So I agree with you that the gap between what we define leadership to be now and what is done by more broadly is larger than ever before. At the same time, how that gap is different is primarily at the node level. I would argue that one of the biggest legacies of ECP, as we're successful, is the ability to run codes on more than just NVIDIA GPUs, to include AMD and Intel GPUs, and in just one node, right? You don't need an exascale system to realize the benefit of portability across these different devices. And so in that way, I think very early on, after ECP is over, assuming that AMD and Intel, continue to push forward with these product lines, what we're providing here is very valuable, even if you're on a desktop system with, a variety of GPUs. And I think we're improving the marketplace by that, by in a sense, kind of creating competition a little bit, making competitive products alternatives to NVIDIA. So I don't know, that's one thought that comes to mind.
Andrew?
I agree with him. Like I said, are you also interested in a vision for sustainability? Was that part of your question?
Well, I am, absolutely. I think
Yeah.
sustainability is, especially with that gap in place, but just in general, when we talk about industry adoption, there's a little bit of a chicken and the egg going on. Industry wants to know that there will be a support model for the long term. And perhaps there's some question as to how much it will be adopted before somebody would get in the business of supporting it. So I think that's one of the kind of challenge I'm talking about for sustainability.
Yeah, so that's a real challenge on the application. And we had a whole session on it a couple of hours ago. And I would say there's no current coherent guarantee. I think I could go through the application portfolio and talk about the extreme likelihood of a long investment in a number of the projects, but there's no single agency who has a vision for what is mission critical and a long-term commitment to fund that independent of anything else. It's still a largely competitive process that's distributed across many agencies, and that is a risk for adopting applications. That said, I still don't think that you would typically adopt one of these ECP applications as a black box that you just need to work. I think it would have to require very deep interaction with the source code and experts to study the numerics and study the implementations on GPUs and probably adopt large pieces of them for themselves so that they become the sustainers of it. And I'm not saying that's always the case. There could be things, there are always examples of things that are more robust than that and there are certain physics components that are well enough understood that you could reduce them to something that you can just sort of use. And that's why commercial companies sell CFD tools and structural mechanics tools and stuff. But a lot of this is very complex, one-of-a-kind multi-physics stuff that you can't avoid having to understand in order to adopt. And I think that kind of lessens a little bit the risk of not having an external support model. I think that's a little different in that regard, right? We use a programming model who want to know the programming model is going to continue to be supported for the next 15 or 20 years, ideally. And I don't know, Mike, I don't know if it looks any different on that end of things.
Yeah, just a few more thoughts that came to mind I think a prerequisite for sustainability of what we're doing is that we continue to see, a diversity of node architectures, let's say we don't all collapse back down to NVIDIA only for GPU, right? That we see this robust adoption of the GPU platforms we're targeting, and other things like we see data flow architectures becoming interesting, right? And as you have this diversity of nodes where concurrency levels have to be really high. That's the only way we're getting any performance boost anymore, at least until we see quantum step in for some areas at least. I just don't, I see that a lot of the work that we're doing is laying the ground for the, being able to adapt to whatever parallelism is available on the node, and making a much more rapid adaptation of our software stack to take advantage of those node architectures. And then of course scaling across nodes as well. That's a huge lift that we still have to realize, right? Because we have these multi 10 tera op nodes, and then you somehow have to pass messages between them and hide the latency associated with that. That's a huge lift for a lot of codes. And so if we can trim away all that latency and make use of more than one device or more than one node at a time, that's value added that is really tremendous. So I don't know, I guess unless something really goes awry in the architecture space, so much of the work that's being done is going to have tremendous value going forward. Whether industry or other agencies are ready to tap into that because it's a huge lift on their own to realize it, that will take time, but the value of the work I think is undeniable.
Excellent. Hey, I want to come back to industry adoption in a minute and from a little different angle. But before I do that, you just talked about diversity of architecture. So I wanted to throw a little bit of a curveball here. If you take a look at what industry is doing, I think the biggest thing that's happened in HPC lately is cloud HPC. I can remember just a few years ago when people were saying, well, that's not really HPC, the interconnect, et cetera, et cetera. But now we're seeing things like Amazon Web Services, EFA, delivering very good scaling certainly at industry scale, not necessarily leadership class scale, but it's becoming a really major enabler. So I'm wondering how both of you see the work that you're doing fitting in with that cloud model, or potentially playing into the cloud space and vice versa.
Well, in the ST space, it fits very well. If you look at what we're doing with E4S and containerized versions of the products, we're investing in security metadata around our products, digital signing. We have other ideas for how to protect our supply chain of third-party software that you can really only execute at a portfolio level. It's nearly impossible for any given product to come up with its own R&D to figure out how to do supply chain. It's much, much better done at the portfolio level. I think the more we move to the cloud, the more a lot of the investments that we're making in the software stack make even more sense than they do for an on-site, air-gapped system, where you have a lot of protocols in place and kind of hand-holding going on.
Yeah,
it's a really great point. Go ahead, Andrew.
I agree with what Mike says. Application users will take cycles wherever they can get them. The key is that you need low latency, right? And apparently now not only are GPUs, but low latency optimized HPC interconnects of modest scale are available on the cloud. And that is part of the solution. The more that there's a convergence between the type of systems that are available, and at least subsets of the HPC systems that we target, then I think it will become more and more sort of part of the picture. Don't think it will become the whole picture. I doubt there is a business model in the cloud that would support the levels of computing we see at the leadership compute facilities, but I guess time will tell. But I suspect that there will be a strategy to incorporate into the workflow of applications an option to leverage time on the cloud as well as at these leadership facilities. That's my read on it right now. Of course, things could change.
Yeah, I think that's a good read. I don't feel like people are going to be sort of competing with the leadership scale in the cloud. On the other hand, I think there will be a lot of interest in taking the applications and the technologies to the cloud that come out of this. And I think that's a really key piece of what success could look like.
I agree.
So Uday had a question kind of online about that as well. I don't know.
Yeah. Yeah, there's a question online whether one can try applications on the Azure cloud, and I don't know who would like to take that one. Maybe Andrew, do you want to touch on that one, or
Well,
Mike?
probably Mike. I mean, it depends on what the applications are built on top
Yeah.
of and what the current state of that particular infrastructure is. But I think we're heading in that direction. But go ahead. Mike.
Let me get started, and then if I see Samir Shendi is in the session, and if he's able to unmute and participate, maybe he could say something in more detail. I know in general we have interactions with AWS and with Google Cloud, and they have a particular interest in our software stack because it represents a significant target for them to compile and run and optimize and test on a regular basis. And in essence, we become a kind of platform testing service for them, and they provide us with free hours. I'm unaware of Azure being one of the targets, but maybe Samir knows if that's changed recently, and if he are more details on what I just said. Samir, you go ahead.
So we are working closely with GCP and AWS, and we have a project where we are also building the entire E4S stack using an MPI runtime that is EFA aware. Because of the Elastic Fabric adapter, it's important to have an MPI that supports that, along with the other components, including the Slurm for scheduling the nodes in the AWS environment, as well as looking at the containerization that we already have. So we have an AWS image right now, and it uses the DCV AWS software for a remote desktop as well. So we are doing quite a bit of work with AWS. In fact, multiple tutorials that were held on Monday and will be held on Friday will use this AWS infrastructure. And we are very grateful to them for giving us cloud credits. We are trying to get some traction with Azure as well, but I have not heard back from Microsoft in the same level of interest that they have shown from Amazon and Google. Does that answer your question?
Thank you, Samir.
Yeah, I think it does. I mean, the cloud providers are obviously looking at who can consume a lot of cycles. And
Yes.
in this space, it's really easy to go from zero to a lot of revenue in a relatively short time. So if they can deliver value, that's important. And I'm really pleased to hear, just for folks not aware of it, EFA is the Amazon Web Services interconnect. And it is remarkably effective for, we've traditionally thought of things like InfiniBand and some of these other things, but it's remarkably effective for scaling. So definitely just a fundamental change in the past few years in what cloud can do in this space.
Thank you.
Thank you, Samir.
Sorry, was there a question there? I
Just
thought I
gonna
heard
bring
somebody.
up the point that one thing that came out in the earlier meeting today was that the cloud is really useful for the community use of this software, not so good for the developers because of the need for particular compilers or things like that, or debugging capabilities really are not. So if you're just dealing with the community use of a code or a software package like E4S, I think it's great. If you're actually trying to develop a new jet engine code, it may not be the place you want to develop it, but it may be the place that you want to just make some runs in it.
Yeah, there are pros and cons. I mean, the pro is you never have to wait to get on, but the con is you are dealing. I mean, you're going to want experience on the platforms that you're going to deploy to. So it can go either way, I guess. And David, just a time check. How much time do we have with this segment? Because I want to make sure that we stay in bounds.
Yeah, so we have about 15 minutes left.
Perfect.
And
Okay,
then we'll
great.
wrap up the session. So
sure. So
There's
yeah.
also an interesting comment a little farther in the chat from Uday. Kind of made the statement that obviously making the switch to GPUs is critical for all of this, and wondering if you could comment on the percentage of agencies who switched over and or industry. We do have a couple of agencies on, at least DoDs, and we've got, of course, a number of companies on here. It might be interesting if you have a chance to talk about that or do a quick show of hands.
Yeah, you broke up a little bit there, Susie, for me, so I had a little bit of trouble understanding, but I think the question is really around GPU adoption. Is that right?
Right. Sorry, I don't know why it's breaking up. Look in the chat, and there's one from a question from Uday.
Okay.
Have the government agencies switched over? What percent? What's the percent of industry that's made the switch?
Yeah, I'll bet that's a really hard question to answer. I'm sure industry isn't talking. And I doubt there's any way to really collect the information at the government level. But I would be interested just to get Mike and Andrew's kind of qualitative take on what kind of pull you're seeing GPU versus CPU, recognizing that obviously your primary pull is coming from the leadership class.
Yeah, I mean, it's always a wake-up call for me to go to any conference and realize how much less uptake there is than I thought there was. Because I live in this world where we're all in, and we see a lot of the benefit of it. Obviously, we have a long time horizon to have worked on them, but I would not say that is necessarily representative of even government agencies. I mean, I know from the IAC that there are uneven levels of commitment. Some people are dabbling, some people have a longer term plan, some people are on the sidelines. I mean, obviously everyone on here knows more about industry than I do, but from all the industry council meetings, there seems to be awareness of a massive software cost and a hesitancy to dive in, so there seems to be probing and trying to see, and one of the big questions that I think is at the center of all of this is, if you do dive all in, how much is it going to be a benefit 5 years from now or 10 years from now? So is the divergence in sort of peak performance between GPUs and CPUs something that's going to continue, or have we wrung out most of the sort of free extra performance from GPUs already, and they'll start to plateau, and we'll need to look at specialized architectures or other types of solutions? And these are all really hard questions. And I really like when Mike cautions people against jumping in, because I can, there's a tendency to evangelize when you've seen a lot of successes, but we've had a lot of investments too to have those successes, and everyone's in a different situation. So I can understand the sort of breadth of different points of view on it anyhow, but I would say it's quite uneven. And maybe, and I'd say we're outliers, certainly. That's my
you are definitely, and Mike, if I can just jump in for a second, I think I can speak to a little bit of why you're an outlier. I mean, first of all, you've been all in on GPUs for a long time, right? Before they really had a chance of making financial sense in industry. There's a steep learning curve, and I think this is one of the things that I'm really looking for from ECP is something to help bring down a little bit. And so companies have to really make those kinds of investments. And then just in terms of access, the machines are hot, and they're very expensive in the cloud, relatively speaking. And if you've tried to get GPU-based machines in the cloud lately, you know that all the machine learning guys are using them all. So, so all of these are going to be barriers to entry in the near term. And but I think it's important that the centers continue to drive that, just because I think it is, if you can reduce that learning curve, that uptake curve, that I think would be a fundamental change in your contribution to industry.
Yeah,
in ways that were economically meaningful to businesses. Yep.
I thought I'd give Uday a chance to clarify what he's been typing. So
yeah, sure.
No, I think all of you answered the question, because we want to dip our toe in. We have, machines at GM, but typically we're using commercial codes, and none of the commercial codes are giving us the scaling that we're looking for. I realized that we would have to kind of use E4S or something, and we don't have those kinds of, setup at GM to basically construct like you have developers. And so if you wanted to dip our toe in the multi-physics, because what I saw was very exciting in the two application forums that I saw, the successes. For example, the Pele M usage was great. And of course, the turbine example is great, of fluid structure interaction. If you want to dip our toe in, I think maybe having access to cloud GPUs and to demonstrate in terms of the business return to the GM community of what we can get would be a good ramp into the things that you have developed.
So I have a couple of data points. That one is, so I still have some engagement with the Trilinos project. And about 6 years or so ago, we started, we've always done annual tutorials to various user groups. And 6 years ago, we did one to a group, and all of the stuff we were talking about, they weren't ready to use. And so we just set aside that meeting for a while. Now this year, they're coming back to us in earnest because they're finally ready to do GPU stuff. We talked about GPU stuff 6 years ago. They weren't ready. They weren't ready 5, 4, 3, 2, 1. This year, they're all ready and they want to be a part of it. The other data point I have is I was at a meeting last week and heard a briefing on the Office of Polar Programs for NSF and how their ocean modeling code, they have not been able to improve the resolution of that code for, I think, approaching a decade. And that's because they haven't been able to transform their code base to take advantage of accelerated architectures. They're still on CPU architectures. And so, there are real costs associated with not making this move. But, it takes time, and you can't really make a community go forward until they think it's the right time to go forward.
And the GPUs weren't the focus of the DOE systems because anybody enjoys rewriting their codes fundamentally differently. This was the basic laws of physics to get to an exascale machine in an energy envelope that was, as Al pointed out, considered at all feasible. And unless you were going to look at like 4096-bit vectors or something that we didn't seem reasonable to us, there weren't a lot of alternatives. I mean, the power performance is much, much better. And these have to scale up to 10,000 nodes to get to exascale. So this is the price we paid to push the frontiers. And then I think we learned so much about them that we saw their value more generally downstream, but we do have to remember the cost of other people with huge software investments in CPUs, what that would mean for them. And sometimes it's hard to get out of the more myopic mindset because I sort of live this every day, and I've seen amazing things done on the GPUs, even things you would never imagine could be optimized to that level. But so urging some caution still isn't inappropriate.
Yeah, and it's really how much investment and time it takes to get to those optimizations, I think, is really the thing that it's the thing that concerns industry, right? So I think we probably have time for about one more question. I want to ask you how you think industry can contribute to this process, or how industry can help.
Well, I'll get started, I guess. So if there is a business case for you to start using GPUs and starting to use some of the software layers that we provide, the portability layers, even the IO libraries, things like that, we didn't talk much about, but data compression, that kind of thing, the in situ data management. We have a lot of different, I think, newer technology capabilities that if you're ready to use them, we would love to, to get started. And then, if you find something that's useful already or after that kind of exploration, and you wanted to start, exploring the business model of working with the E4S, commercial support team, and so that you can actually get someone to answer the phone, because we'll do that to some extent, but we can't keep doing it for a long time. Those are ways. Also, by the way, Samir mentioned that our Frank system, our our multi-node thing that has all sorts of devices on it, we can open it up for this kind of trial and error usage. He put it in the chat.
Yeah. So, I mean, I agree it would be hopefully mutually beneficial to first become aware of what we've developed, and then to, if and where appropriate, try to use it, because it is both validation of what we've done as well as helps us understand more its capabilities and limitations. And then I think the idea would be, so Mike talked all about the software technology infrastructure. Within application development, I didn't talk about a special subclass of software technology that sits right next to the applications that we call kind of application level co-design, which is software infrastructure, but it is customized more to the application. And adaptive block structure, adaptive mesh refinement would be one example. Unstructured meshes, particle and cell. So this is the infrastructure for doing very complicated codes built on top of, for example, those mesh structures, without having to deal with any of the direct GPU coding or any of the bookkeeping involved with remeshing and time subcycling and all that stuff. And these components, in several cases, are very well packaged and very well documented and very well tested. And they make it so much easier to be able to take a few, say, PDEs that describe the system you're interested in and go from nothing to an efficient GPU implementation. And I think demonstrations of that would be beneficial for everybody. But I think it starts with awareness. And of course, that falls on us. And I think Mike has a really good strategy, and we could do better in applications to make it clear what we have done, what state it's in, and make it easy to find without having to sort of dig around and guess and interpolate and so forth. But I think that could be good for everybody.
Excellent. All right. Are there other questions from the attendees?
So there was a comment in from Dave Kempinski about how cloud is more of a business model than actual technology.
Yeah, I'm going to, well, I've got an opinion on that, but if anybody else would like to comment. I'm actually going to disagree with my esteemed colleague on that one. I think if you take a look at how cloud fits in, yeah, some of it is things you can do other ways, right? EC2 or is basically computers you can run on. But I think if you take a look at the palette of service-based architectures that are available as Legos that you can snap together into new applications very quickly, that actually does become an enabling technology all its own. So the individual components, maybe not so much, but the overall model, I think is really a game changer.
Right, and I was going to expand on that, Pete. This is Jörg from Boeing. I think the ability to just think about your overall workflow, and this comes back to the earlier meeting, like this morning's meeting. Like, for example, if I want to have like a RESTful API that I run to display data, and I want a Jupyter Notebook server. Yes, I can do that with a traditional HPC, but if I have HPC that's driving the data into object storage once it's computed, and then I can use cloud native development approaches for my visualization or my dashboarding, it's just opens up so many ideas of using Lambda functions to do processing kind of triggered when things come. Could you do all that with the traditional HPC system? Yes. And then, of course, the other part is, when you deploy an on-prem HPC system, you make an upfront decision exactly what configuration to get.
Yep.
And it's a global decision. In cloud, I can use 5 different processor types depending on what my application likes. Like if I have an application that is more clock sensitive, yeah, I'm going to get the node type that has the higher clock speed. I would not do that for an on-prem system. So my tail of applications that maybe only represent 10% of my usage, so would never drive the design of the system, now all of a sudden get a system that's really optimized for what they like.
Yeah.
And then on top of that, the ideas about batching, right? So a lot of the stuff that I at least see on our system, or some of the stuff I see on our systems, is just like Monte Carlo simulations where I need to run hundreds of thousands or millions of single-threaded applications. Again, I can do this on an HPC system, but I don't really need everything that an HPC system provides. So
Yeah.
I think you can there's just a lot of opportunities to rethink how you do things.
Yeah, and Jorg, I want to bring it back around a little bit, but I do think what Jorg has just mentioned in terms of the low end distributed job sort of disappearing from the HPC system is a really important aspect of this. You know, you can now, if you can make something a Lambda and blow out 100,000 of them at once, right? All of a sudden you don't need to run that on your HPC and burn it down over, you know, several hours or something like that. So maybe that is a shift toward the higher end. Mike and Andrew, I don't know if you have any additional thoughts on that.
Lambdas are greatly portable, right? And I mean, as a concept, right? I mean, that's the fundamental building block for even on the HPC systems, not in the same way you're saying, but as a general notion, right? Of you know, the Lambda expression as a stateless item that you can run many instances of it. So, but yeah, I don't. As far as like small jobs and such, I think you're probably right. I mean, what are the big benefits we get out of these? You know, the leadership class systems is, you know, I like the phrase, and I can't remember which meeting we were in, but this highly curated computing, this notion of highly curated computing, which is what we get when we have a leadership class system. You know, that we have, you know, a lot of support for doing, you know, the really ambitious jobs. And that's what our leadership platforms will be used for, I think, going forward.
Exactly, Mike. Hey, Pete, I think you actually kind of agreed with my comment earlier, by the way, before you disagreed.
All right.
And I'll tell you the words you used when you agreed with it. You said that when you start looking at putting together the Legos for your GPU accelerated heterogeneous system and trying to get to the same type of InfiniBand 11 and in the future better backbone, and then high speed data transfers for storage, you are unable with AWS and Microsoft Azure. Well, first of all, they don't even have a technology architecture that's templated to give you. I can tell you that today because I've recently even re-asked both of them to just show me, you know, the technology architecture that you have templated that would equal, you know, a leadership class system that would be at an industry level. And then you said it, you know, when we start adding the heterogeneous nature of what we're talking about here, GPU accelerated, which there is a lot of even ISV software now today, Cascade, Ansys, that they have already been doing tremendous development. And if you don't have a GPU accelerated system, you're not going to be able to take advantage of it. But if you do, you can already take advantage of it this year, now, as a matter of fact. And so you now know that AWS and Microsoft Azure, to put that system together, there's two things. One is you have to create the architecture to then converge on what is, you know, something analogous to smaller scale, but leadership class type of computing. And in order to do that, they want you to buy into a long-term plan with them, not just scale up and scale down, you know, ubiquitous compute, but they in fact want you to, contract into a 3-5 year commitment, which then turns into not a whole lot different than if you were on an on-prem or call it a private cloud, because all of your compute is in one spot. It's not all over, it's in one spot. And then the other piece that we won't even get into today, but it's the fun cost on discussion on cost, which I think because when you start even piecing together the GPU accelerated side, the cost is the business model portion that I mentioned. There will be a day when those two and others decide to bring those costs down. And we all need to be cognizant of that. And then when the technology and the business model begin to converge so that we can create high-end cloud computing, then it'll get really interesting. But right now, in order to build, construct, operate this type of leadership class system, plus the integrated tool set that goes on top of it. Because if you want to do high volume, the amount of modeling and simulation that people do in industry, you're not running handfuls of jobs. You're running thousands of jobs or hundreds of thousands of jobs. We're actually running millions of jobs now on our high performance computing, millions of jobs on an annualized basis. So when you're running millions of jobs, you have to have an integrated tool chain that runs on top of that, let's say, cloud computing. And that integrated tool chain end to end, from what you put in to what is pre and post process, to what is stored, to what is visualized and how it's visualized through some type of virtual desktop infrastructure. It's not portable between cloud systems today. You can't take that integrated tool chain and just go, oh, now I'm going to run it on Azure. Now I'm going to run it on AWS. Now I'm going to run it on Google. So, and I see Al kind of, listening in as I'm saying this, but they're just not portable yet today. And that's another portion of the business model, not the technology, but the business model and cost that goes into it. Now, I know I've said a lot here on kind of responding to that one, but, as this cloud discussion kind of plays out, there's a bunch of pieces that come together in terms of the business model, the technology, and then the trade-offs between them.
Yeah, and I just want to be very clear. I'm not suggesting for a moment that the cloud is ever going to be, well, Art, I should be really careful about saying never, but I don't believe the cloud is really going to be a substitute for the leadership class centers at any time in my career, if ever. But I do think that the centers and the work like we're discussing today, combined with the value of the cloud to industry, can really be revolutionary in terms of what industrial HPC looks like. So we want to be thinking about those things and thinking about that on-ramp for some of these tools, because really the challenge to innovation is about software, right? A lot of times when we're talking about high-end modeling, right, there are problems that we need to solve today, things that we can't simulate today. And going off and writing that software is a very daunting proposition from a dollars and time perspective.
Totally agree. Totally agree.
So
and Mike had some good inputs on that too, where he in his software stack and around containerization is really making this onboarding and future on-ramp for both, if we think about it.
Yeah. So I think that flow back to industry can just really change the world. It's I'm not overstating that. So excellent.
So we should probably kind of wrap up now. We're a bit past our time, and I think especially people on the East Coast are probably much.
As soon as you start talking cloud, everybody could talk all day. So let's roll it up. I just want to first of all thank Andrew and Mike for their insights and the work they're doing, and for all the people who contributed today. It's great to see a few of these folks who I haven't seen in the past couple of COVID years also. So But anyway, really great discussion, and you know, I'm just really excited. I think about the focus on influencing the outside world through software that's inherent in the ECP program and baked into it. So really good stuff.
And it's all the work of the hundreds of other people who are at this meeting. Really, that they're the people doing all the real work. So thank you to them. A few of them are on here, so I'd say thank you to them.
Excellent, excellent. Well,
Mike, thank you very much. I think Andrew already had to drop off. And Pete, we thank you very much for moderating today. It was great to have an industry perspective.
all right, thank you so much for having me.
Yeah.
Yeah,
very
thanks,
good.
Pete, for keeping us moving and lots of interesting discussion. So,
Excellent.
all right.
All right. Thank
Thanks,
you,
everybody.
everyone.
We'll see you all tomorrow.
Ciao.
Bye.